This is our video to review for Chapter 9 and 10 test, so you can advance to whichever problems you would like to hear more about, or you can watch the entire video. So in number 1, we already have our quadratic in the form of blob squared equals a constant, so we can simply take the square roots of both sides, and this will become plus or minus 2i. So we get two complex answers, and you could leave them in this form. As opposed to number 2, where we take the square roots of both sides, we get two real answers. But you have to remember when you do the square roots, you get two answers. And then we want to solve for x, so we're going to subtract 1 from both sides. And then we're going to divide that by 2, and you can do this in a couple different orders of the steps. But if I write it this way, then you can see that this is negative 1 plus 5, and then divide by 2, and it is negative 1 minus 5 divided by 2. So we would get a 4 divided by 2 is a 2, and a negative 6 divided by 2 is a negative 3. So we could write our solution set with a comma between. In question 3, this will be given perhaps in multiple choice format, but we know the sequence of steps. So if we were going to complete the square, we already have a equal to 1. So we would complete the trinomial, and our constant is already on the opposite side. So remember what we did. We took half of the middle coefficient and we squared it. So we would add a 49 to both sides. So of the multiple choice options, you would look for the one that would say add 49 to both sides. Question 4 is a little bit different because the a value is not equal to 1. So our very first steps would be a little different. So we need to move the 6 to the other side, add 6 to both sides, and then it would look like this. And then we would divide by 2 to set our a value equal to 1. So we would divide all of the terms by 2. And then what do we want to add to both sides? It looks like I cut that off here. So we would take half of our middle coefficient. So half of this term would be negative 5 halves. And then we would square it. That's what we would have to add to both sides. We would have to add 25 over 4 to both sides. And then we could finish the complete the square process. All right. Solve by quadratic formula. So we need to get this in ax plus by equals c form first. So we need to add 5 to set it equal to 0. So our a value is 1, our b value is negative 2, our c value is 5. So in quadratic formula, our answers for x will be equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. And then we do a little bit of arithmetic here. We see that we have 4 minus 20. 4 minus 20. So we would have a discriminant. Remember, the term under the radical is called discriminant. And then we can do some simplifying. So this term is going to become plus n minus 4i over 2. And then I would like you to separate the real and the imaginary part. So I would like you to take 2 divided by 2 to get a 1, and then 4i divided by 2 to get a plus or minus 2i. So remember, in standard form, a complex number was a plus or minus bi, and that's why I would prefer that you split that up. All right, number 6, we've seen one like this before, and I think it bothered some students. So let's read carefully. K is a negative number. So perhaps the easiest thing you might do is pick a negative number. So what if K was -5? So if we put a -5 in for that value of K, would you get imaginary solutions? So yes, you would, because you would be taking, oh, I'm sorry, let me back up. Better erase. I just covered up a negative sign. Let's be careful here. K itself is -5. So this expression for A already has an opposite sign there. So I better be careful to write that opposite sign and then K. So I was wrong a minute ago. That value is +5. So we would do the square roots of both sides and we would get irrational answers, but they wouldn't be imaginary. So let's check some of the others. If K is a negative number, and my example was -5, what would B look like? It would look like 2x squared minus 25 equals 0. And when we move the 25 to the other side, it would be positive. So again, there's no, when we take the square roots here in a minute, we would be taking the square roots of positives. So there would not be an I in this term either. So let's take a look at C. One of these eventually will give us a negative answer. So again, I'm still testing here what happens if we put a -5 in C. And you don't have to write this, by the way. You would just be looking at this to answer the question. So here we would move this so it was a plus. So this plus sign and the negative is coming from the 5. So when I move it to the other side, it would be +5. And again, I can stop at this point because we can see that there would be a positive number under the square root. So let's find out if D is going to be our answer. So in letter D, for the K value, I'm thinking -5 as an example, simply as an example of a negative number. So if we moved the 3x squared term to the other side to make it positive, and we divided by 3, then our next step would be taking the square roots of a negative number. And that's enough to answer our question. We didn't need to find the answer. We just needed to find which one will have 2 imaginary answers. And we've actually found them here. This would be the square root of 5/3 times I would be our 2 answers. So our 2 imaginary answers would come from letter D. Question 7, and instead of matching, these might be given as 4 separate multiple choice questions in test format. But let's remember what the discriminant is. That's the part of the quadratic formula under the square root. So because it's beneath a square root sign, if it is a negative number, then we just found out that we get imaginary answers. If the discriminant is 0, then the only part of the quadratic formula that would be left, let's take a look at it again. If the discriminant is equal to 0, then the only thing that would be left in our quadratic formula would be the -b/2a. So if the discriminant is 0. If the discriminant is a perfect square, then the radical would go away and we'd get 2 rational numbers. And if the discriminant is a positive number but not a perfect square, then we're going to get 2 irrational answers. So let's go through each of these and see if we can clarify. So our discriminant, we simply need to take our b squared. So our -4 squared minus 4 times a, 4 times a, which is 4, times c, which is 1. So here we have 16 minus 16, or 0. So that's the case where our discriminant term would be 0 and disappear. So we would only have negative b over 2a left as one rational answer. So this is going to be option C. In the next one, we would take our b squared would become positive 4 minus 4 times a is 4 times c is 1. So now we have 4 minus 16. So we would get a negative 12. And when we take the square root of a negative 12, we would get our two imaginary answers. And our next problem, if we did b squared, we would have 4 minus 4 times a is 4 times c is negative 1. And here we would get positive, so we would have a 4 plus 16. So that would become 20. So again, under the radical, if you had a 20, the square root of 20 would give us 2 radical 5. So we would have the plus minus. So we would get 2 irrational answers. And the last one, we would take b squared would be 16. B is negative 4. Minus 4 times a times c. And here we have, oh, it looks like I have a repeat of the first one. And I don't think I wanted that. I'm going to pause and see if I should change that problem. All right, so on my copy, I have a typing error here. Hopefully you have a 3 on your paper. So let's try this again. We would have b squared is 16 minus 4 times a is 4 times c, which would be 3. So here we would have 16 and, oops, negative 3, sorry, negative 3. So we'd have a negative times a negative would be positive. 16 times 3 is 48, and that is 64, which is a perfect square. So again, we're looking at the discriminant. The square root would give us an 8, so we would have a plus or minus 8, and we would get 2 rational roots. All right, sorry for that error. Let's put 3 graphs here on the same axis. Our basic graph for the square root of x, you know the square root of 0 is 0. You know the square root of 1 is 1. The square root of 4 is 2. Let me label these. You might be given this problem in multiple choice form. Now what we want to do are a couple transformations. So remember here, if we're going to subtract 3 from the x, you should choose 3 larger values. So you should move 3 units to the right. So each of these points is going to move 3 units to the right. So exactly the same graph, but it would start at 3, 0. And so that's our graph of g of x. And I could label my first graph here was our f of x. And let me switch colors. Let's do h of x. This should not have a question mark there. It should say square root of x minus 3. So this is down 3 units. So it's our black graph was our original. And we're moving each point down 3 units. So we would start at 0, negative 3. And then it would be the same shape as the black graph, and that would be our h of x. And those might be given again in multiple choice form, so it would be even faster than if you had to graph them yourself. All right, let's remember what the absolute value graph looks like. The absolute value of negative numbers become positive. So we get an absolute value graph. Looks like a piecewise function, pieces of 2 different lines. And then we do some transformations. So in function g, we're going to multiply by 1/2. So it is only going to, it's going to get wider, going to grow slowly. And we're moving it up 5 units. So let me choose here. I didn't give you much space here. Let's say that, and I'm not being very precise here. Again, it would probably be multiple choice. So as long as you tell that the graph was wider and had an intercept at 5. And our third graph, h of x, we are moving the x2 to the left. So we're going 2 to the left, and then we're subtracting 3. So hopefully these transformations are much easier. So our green graph was our original. So remember that we're using our 0, 0 point here, but we're moving to the left 2 units, and we're moving down 3 units. And again, check to make sure whether there's a vertical reflection or if it's wider. So here our multiplier is just 1, so it's the same shape as our green graph. Same shape as the green graph. It just has a different corner at -2, -3. Describe the orientation of the parabola. And this is our graphing form. Remember that f of x, you could put a y in that position. And now I'm going to do an example here. It says that a is a negative number. So instead of f of x, I put y. A is a negative number less than 0, so I'm just going to pick one. I'm going to put -2. H is a positive number. So to make this easier, I'm going to replace. So the negative is from the equation. I'm going to replace that h with a positive number like 5. And our k value is less than 0. So it says plus k, so I'm going to be real careful here and put plus a -1. Of course, you could put subtraction. All right, so you can see where our vertex would be. We took this graph and we moved it 5 to the right, 5 units to the right. And outside the function here, outside the parentheses, we are moving it down 1 unit. So what we know about the vertex, instead of being at the origin, our vertex is at 5, -1. And what do we know? Because a is negative, we know that it opens down. It's a vertical reflection, and it's doubled, so it is narrower than our basic parabola. So now we want to find the choice that matches that. Our parabola opens down would be choices C and D. Let's choose from those. Its vertex is at 5, -1. So again, the quadrants here, remember, are numbered 1, 2, 3, 4. So our vertex is in quadrant 4, and the parabola opens down. So it looks like that's our correct choice. All right, let's do some graphing. This was called general form. Ax plus by equals, ax squared plus bx plus c is general form of a quadratic. And our formula for the vertex from general form is the first part of the quadratic formula, the -b over 2a. So we take the values from our coefficients. So b is 2, so we take the opposite of 2 divided by 2 times a. A is equal to 1, so b over 2a gives us our x-coordinate of our vertex. So now I know that that would be a -1. And then we plug it into our function to find the y-coordinate. Put 1 in for x, and we get 1 squared plus 2 times 1 plus 1. So we would come up with 4 as the x-coordinate, or as the y-coordinate of the vertex. We know because a is +1 that this parabola opens up and has its normal shape. Oops, that's a little too wide. Don't worry too much about that. I can check that a little bit better in a minute. So maybe let's As long as I erase that, let's make the point that here we're going to be doing the y-intercept. So to find the y-intercept, let's let x equal 0. So f of x, when we put 0 in, f of 0, 0 squared plus 2 times 0 plus 1, we can see that this value of c is our intercept. So I think I have a sign error. I'm going to double check. Did I put -1 into the function up here? So how did I catch my mistake? I caught my mistake because I got a y-intercept down here and a vertex up there. So that doesn't work. If the parabola opened up, I would miss the y-intercept. So I can double check. This was my error right here. Our coordinate was -1, not +1. My mistake again. All right, let's find out here. This would be a 1 minus a 2 plus a 1. So it looks like the x-coordinate or the y-coordinate of our vertex should have been 0. Let's get that fixed up. The y-coordinate of our vertex is 0. Now that looks like our basic parabola. So that's a good way to catch your mistakes if you did the same thing I did. And that parabola can be folded in half. Its axis of symmetry is always through the vertex, so a vertical line. And now we're doing a parabola in standard graphing form, standard or graphing form. And it was one that uses our transformations, which hopefully we've practiced often enough. Hopefully now you know that our basic parabola has its vertex at 0, 0. That is our y equals x squared basic parabola. So here we are moving that parabola to the right unit, our horizontal shift in the opposite direction, and up 2 units. So we know that our vertex is at the opposite of this value and the same sign as that value. So our vertex of our parabola is at 1, 2. This parabola is open down because a is negative. So I could just sketch my basic parabola, or you could stop and find the y-intercept. So to find this y-intercept, you could let x be equal to 0. So we would have y is equal to opposite of 0 minus 1 squared plus 2. When we square -1, we get +1, but then we do the opposite sign. So we would get -1 plus 2. So our intercept is at 0, 1, and that would help you with the how wide or how narrow. And we know that again, our axis of symmetry always goes right through the vertex. So now let me just label that vertex and that intercept. And the equation of the axis of symmetry is x equals 1. And our next parabola has y squared instead of x squared. So we better remember our basic parabola. When the y is squared and not the x, then our parabola, remember, turns sideways. So now we have to be careful with our transformations that now what we're shifting is the y coordinate. So inside the parentheses, we still go in the opposite direction, but this time it's changing the y coordinate. So we would have to choose y to be 4 larger. So we're actually going to move this up 4, and this is changing the x coordinate. So it is moving the x coordinate to the right. So it's exactly the same idea, but you have to say that this change is moving the y, and this change is moving the x. So our vertex, we still take the opposite of the number inside the parentheses, but that's our y-coordinate, and we still take the same sign as the value outside the parentheses, but that is our x-coordinate. So our vertex is at 3, 4, and our parabola is sideways because the y is squared, and it has an a value of -1, so it is going to open to the left. And you might say, now how wide or narrow should I make that? Well, let's find an x-intercept. To find an x-intercept, let's let y be equal to 0. So we would have a 0 minus 4 squared plus 3. So here we would have a -16 plus 3, or a -13. So that's our x-intercept. So it's way over here. So our parabola is going to, and I kind of missed there, our parabola is going to be going this way. So we had our vertex at 3, 4, and our x-intercept, we let the y-coordinate be 0, and we found the x-intercept to be -13. Our axis of symmetry, I have kind of a weird looking parabola there. We'll let it go. So our axis of symmetry, I guess I better make that look more like a parabola. Our axis of symmetry goes right through the vertex. It's a horizontal line through this point, so it is y equals 4. All right, our graphs that we've been working on, we know that our basic parabola has symmetry to the y-axis. Our cubic function, we worked on this. We know that 2 cubed is 8, if you've forgotten, and we know that -2 cubed is -8. And we know that 1 cubed is 1, and -1 cubed is -1. So if you remember, this curve was what our y equals x cubed looked like. And because when we put in opposite values of x, we got the opposite values of y. So our definition for that kind of symmetry, when we put in the opposite value of x, we got the opposite value. So usually students find it easier to think about the graph than looking at this algebraic definition. But we know that quadrant 1 pairs up to quadrant 3. That was called origin symmetry. And our sideways parabola, x equals y squared, of course, has symmetry to the x-axis. When do we have all three? The only one we've done is equations of a circle. X squared plus y squared equals 9 has all three symmetries. All right. Intervals of increasing and decreasing is always as you're moving from left to right. So if I was going to trace over this function, do you see that my stylus is increasing as I move from left to right? So until we get to 0, so from -infinity to 0, that graph was increasing. And then when I'm here, how do I get to the next point? I go horizontally, so it's staying constant. So we would say that it is constant over the interval from 0 to 2. And then when I continue, I would jump up here. And how would I have to move the stylus? I would have to be moving down. So we're decreasing as we move from 2 to infinity. So rising is increasing. Oh, decreasing and constant I wrote in the wrong spots. Decreasing and constant, sorry. All right, so rising and falling. So you've already done this when you graph lines. Again, just simply remember that, oh, now I put that a little too close, it's in between there. increasing, rising, decreasing, falling. Make sure you can see which one I meant there. And constant is horizontal. Always reading from left to right. Always left to right. All right, so here we have a piecewise function, two different pieces. So we want a graph. Remember, f of x is just another name for y. Y is equal to negative x plus 2. If I graph that entire line, it has a slope of negative 1. So we would go down 1 and over 1, starting at our y-intercept, down 1 and over 1. So we would have this falling line if I graphed the entire line. But I don't want the entire line. We have its domain is only the values where x is less than 1. So I find this point right here, and I only keep this part of the line when x is less than 1. Oh, and I should make that an empty circle because it doesn't say equal to. So let's make that an open circle. And now I'm ready to graph the second part. Remember what this says, y is equal to negative 3. That is a horizontal line, and its domain is when x is greater than or equal to 1. So that part of the line is where I will have the solid circle because the equal to is included. So you're keeping halves of two different lines. If we have something squared, will it be bigger than 1? Always. Anything squared will be at least not bigger than 1. It'll be at least 0. So that would be all real numbers. Is a square of anything ever going to be less than negative 2? That cannot happen. And here we need to find our critical points are the values that make this equal to 0. So if x was equal to 5, or if x was equal to 5 halves, or if x was equal to negative 9, those would be the three values that would make this equal to 0. So those are the turning points. Every time you cross a critical number, 5 halves is 2.5 if you prefer. Every time you cross a critical number, one of those factors will change signs. So remember what we did was we tested a number in each interval. So here I might test x equals negative 10. Here I might test x is equal to 0. In this interval, I might test x is equal to 3. And here I might pick x is equal to 27 to show you that it doesn't matter. Pick any number in the interval. And now what we're doing is plugging the number into this inequality. So let's think if I put negative 10 into the first parenthesis, it would be negative 15. I'm only going to write down the negative sign. If I put negative 10 into the second parenthesis, I would get negative 25, and I'm only going to put down the negative. And if I put negative 10 into the third parenthesis, we would have a negative 1. So all three parentheses are negative. So when we multiply them, our desire here, our goal, is to get a product less than 0. When I multiply three negatives, it is true. It is less than 0. So we want a parenthesis because it is strictly less than 0, not a square bracket. So parenthesis is an open endpoint, and then I would draw an arrow going to the left forever. So now I think it's going to be false in the next interval. If I put 0 into the first parenthesis, I would get negative 5. Put 0 in the second parenthesis, and I would get a negative 5. Put 0 in the third parenthesis, and now I'd get a positive 9. So when I multiply, is that less than 0? That would be false. That would be false. So we expect the next one might work. If I put 3 in for x, the first parenthesis would be negative 2. The second parenthesis would be +1, and the third parenthesis would be positive. So if I multiply 1 negative and 2 positives, it is less than 0. So as we expected, now it works again. And if I test the last region, I think it will be false. If I put 27 in those parentheses, all three will be positive values. The product of three positives is not less than 0. So that would be false. So we do not graph the false regions, and we do graph the true regions. All right, that was a marathon, but I think we've finished.